So, good morning, everybody. I'm very glad to participate to this workshop. And let me first thank Ingo and Dimitri for their kind invitation. So I have the honor to open with my presentation, and I will share with you our results about frequency comb generation in quadratically nonlinear Bach resonators. So optical frequency combs continue to attract a lot of interest because they are the key ingredients in many important applications. They constitute precise frequency ruler for frequency metrology, or they can provide simultaneously lots of lasers for high-resolution spectroscopy, and they can open new venues for the generation and control of complex quantum states. So traditionally, optical frequency combs have been generated inside ultra-fast moduloc lasers, but recently also quantum cascade lasers have been engineered in order to emit broad and powerful frequency combs. But besides laser generation, there is another way to generate an optical frequency comb, and it is the parametric interaction between a continuous pump and a nonlinear microresonator. In particular, Kerr microresonators very simplified the experimental schemes and paved the way for integrated comb synthesizers. So we start with the brief fundamentals. These are some beautiful images of different types of Kerr microresonators. We can see chip-based silicon nitride, or toroidal or millimeter-sized crystalline microresonators. And the plot shows the great result obtained by Kippenberg's group in 2007 in the generation of a broad frequency comb in the telecom range. But what happens in particular when we shine a light on a microresonator? The first process occurring in a microresonator when a continuous pump interacts with it is a modulation instability, which is driven by a four-wave mixing. So at the beginning, the only frequency present in our system is the pump frequency, but then two pump frequencies are combined in order to emit two new frequencies, the signal and idler. And this is the first crucial process. Then other cascaded four-wave mixing processes lead to the formation of a new sidebands around the pump, up to the formation of an optical frequency comb. And what about K2 processes? It was already known since the 60s that the cascaded K2 processes could mimic K3 nonlinearities. And in 2015, 6 years ago, we demonstrated the possibility to generate optical frequency combs in optical resonators by the exploitation of pure K2 nonlinear processes. So these quadratic combs could have several advantages with respect to Kerr combs, as for example, the possibility to exploit the inherently higher efficiency of K2 processes. This efficiency can be spectrally tailored over the whole transparency range of the crystal. And another crucial feature is that when you deal with a frequency comb and you generate it not only around the pump, but also simultaneously in spectral regions far away from the pump. So in this talk, I'm going to introduce to the physics of K2 combs, starting in particular from our first experimental realization of an optical frequency comb in a simple intracavity second harmonic generation. So I will show you the first experimental results and the theoretical model that we developed to unveil the physics of K2 combs. We also explored the possibility to generate frequency comb inside an optical parametric oscillator, and I will show the experimental results that we obtained with this scheme. And in the final part of the talk, I would like to show you our latest results about frequency comb generation in a doubly resonant second harmonic generation system. In this system in particular, we were able to manage different emission regimes, and in a particular regimes where only twin beams are generated, we were able to observe quantum correlation. So this is the first scheme that we use to generate a frequency comb. It is a cavity initially conceived for the generation of the second harmonic of a neodymium YAG laser at 1 micron. So this is a bulk system. We have a bow tie cavity with 4 mirrors, 2 plane and 2 curves. The periodically poled lithium niobate crystal is put between the 2 curved mirrors, and this is an image of the cavity. So this is a bulk system, not so little, but it gives us the possibility to easily change some crucial parameters as the size of the beam inside the crystal, or the distance between the mirrors, so the free spectral range and the thief separation of the comps, or the power coupling to the cavity. The cavity has also a PZT on one of the mirrors, which can change the cavity length, and we lock the cavity to the laser frequency through the use of this PZT. Then we have different diagnostic systems to analyze the comb generated. There's a spectrum analyzer, radio frequency spectrum analyzer, and optical spectrum analyzers. So during second harmonic generation, we noticed that in the correspondence of a certain pump power, the second harmonic power clamped at a constant value, irrespective of the increasing pump power, and this happened because the second harmonic itself was pumping a cascading nonlinear process, and in particular an optical parametric oscillator. So the diagram here shows the basic processes happening in the cavity. First of all, we have the generation of the second harmonic. So two pump photons are combined to generate the second harmonic. The second harmonic itself pumps an internally pumped optical parametric oscillator, and so two new frequencies are generated, which are called signal and idler. And if we look at the energy level diagram here, we can see that the cascaded process of a second harmonic and internally pumped DPO can be seen as a net energy transfer from the pump to the signal and idler photons mediated by virtual second harmonic photons. And this process is totally analogous to a four-wave mixing that I have shown you before. And these are the experimental results. We obtained the different regimes of comb generation according to the phase matching condition for the green radiation. So this plot here shows the combs obtained when the crystal is phase matched for second harmonic for increasing pump power. So we start from the rising of two sidebands for 100 of milliwatt of power, then increasing the pump power, we obtain multiple sidebands at a distance of around 1 nanometer from the pump. And in the correspondence of the maximum available power of 9 watt, we have the generation of secondary combs around the primary combs. A different comb structure has been obtained when the crystal is out of phase matching, and as we can see here, in the correspondence of the maximum pump power, we got the minimum thief separation, which is equal to the cavity free spectral range, and we verified it by detecting the bit note at the cavity free spectral range. Interestingly, we detected this bit note not only at fundamental frequency, but also in the visible range at the second harmonic frequency, demonstrating the simultaneous generation of the comb around the fundamental and the second harmonic. So besides experimental results, we derived the first simple theoretical model in order to unveil the physics of Chi2 comb formation. And this scheme describes the basic process that we want to describe with the model. So we have the second harmonic. The second harmonic itself pumps an internally pumped optical parametric oscillator, and then through successive second harmonic and some frequency generation processes, we are able to transfer energy from the subharmonic to the harmonic region. And here are the three-wave couple mode equations that we derived. They are three equations for the three subharmonic frequencies, so the pump, the signal, and idler, while the harmonic fields are sleeved first variables, so totally follow the dynamics of the subharmonic fields. As we can see, we have a third-order nonlinear interaction mediated by this coefficient, which describe the couple of cascaded processes. So these equations can give a full description of the elemental dynamics of the cascaded system of second harmonic and optical parametric oscillator. So successfully, we derived a generalized couple mode equation, and this equation now is valid for any number of interacting frequencies. And as we can see, we can have a very striking analogy with the equations that govern Kerr combs, because we have third order interaction mediated by this coefficient eta that, as I said before, describe the couple of cascaded second order nonlinear processes and mimic efficient third order coupling processes. We also derived, in collaboration in particular with François Léo, who is here at the workshop, Mirror Quintalo from University of Auckland, Tobias Henson, and Professor Wabnitz, who will shed light on all these aspects. We derived a time domain model, which is based on an infinite dimensional map for the field amplitudes. So this map is constituted by two equations for the propagation of the subharmonic and the harmonic field inside the nonlinear crystal. And these are standard equations of propagation in which we added the dispersion terms. So we have the group velocity dispersion of the fundamental and the second harmonic, and also the GVD, the group velocity mismatch, the Wolkoff term, which is very important in conformation. So these two equations are completed by the boundary conditions, which relate the fields between different round trips. And as we can see, by changing the boundary condition, we can describe not only a singly resonant second harmonic generation process, but also a doubly resonant second harmonic process or an optical parametric oscillator. So in the mean field approximation from these two equations, we can derive a single mean field equation, which is very powerful in describing the spectral and temporal dynamics of the combs. And again, we find a very striking similarity with Kerr combs because we have a third order nonlinear interaction. But here we can also find a non-instantaneous interaction, which is linked to the presence of the temporal work-off between the fundamental and the second harmonic, and this is typical of Chi2 combs. Also, as Professor Wabnitz will describe in detail, the stability analysis is very important to understand comb formation in Chi2 systems. So besides second harmonic generation, can we generate a frequency comb inside an optical parametric oscillator? And the answer is yes. We generated a comb in a degenerate optical parametric oscillator. This is the scheme. Our OPO is based again on a cavity which has the same geometry of the second harmonic cavity. So we have a bow tie cavity with a periodically poled lithium niobate crystal inside. And the OPO is pumped by a frequency doubled neodymium YAG laser at 532 nanometers and emits the generate frequencies of a signal and Adler at 1 micron. Even in this case, the cavity length is controlled by a piezoelectric actuator, and we have different diagnostic systems to observe the frequency combs. And these are the experimental results. In this scheme, in particular, we were able to slightly change the laser cavity detuning. So the frequency detuning here is measured in a unit of cavity line width. And as we can see, we obtained different types of combs in the correspondings of different detunings. In particular, for the comb on the upper left side, we were able to detect again a bit note in the infrared region and also a bit note in the visible region. And this indicates that we are generating a comb around the visible pump this time and around the subharmonic region. So this is quite interesting because it is a proof of principle demonstration that we can access the mid-IR region with a frequency comb starting with a pump in the near infrared region. And here I also show a comparison between experiment and theory. These simulations are obtained by the integration of the numerical equations that describe the comb. And as we can see, we got quite a good agreement between experiment and theory. So in this last part of my talk, I would like to show you our latest results about frequency comb generation in another Chi2 process, which is a second harmonic generation intracavity, but this time we are dealing with a doubly resonant system. So the previous systems were based on systems in which only one frequency could resonate as the fundamental in the second harmonic generation or the subharmonic signal and Adler in the generate OPO. Now we wanted to work with a system in which both the fundamental and the second harmonic could resonate simultaneously, and this is much similar to microresonators. So this system is very interesting because it shows a milliwatt level threshold for comb generation, much lower than the several tens of milliwatt of the previous systems. So it gives us the possibility to reduce the pump power, and also the system has a very rich dynamics, and in a particular emission regime, we were able to make our first observation of quantum noise reduction. This is the experimental setup. So the cavity has the same geometry as the one I showed you before. And this time all the mirrors have high reflective coatings at both the wavelengths, except for this output coupler, which has a partial reflectivity at both the wavelengths. We also inserted in the cavity a few silica windows in order to manage the different conditions of resonance. So by carefully rotating this window, we can put on resonance both the fundamental and the second harmonic. And in this system, we also realized a very robust locking system, a boundary overall offset locking technique, which permitted us to control the detunings up to several cavity line widths. In particular, this locking system is based on an auxiliary beam, which is orthogonally polarized with respect to the pump beam, and is injected in the cavity in the opposite direction with respect to the pump. So this plot here shows how our locking system works. We have the counter-propagating auxiliary beam, which is the light blue signal, which is phase modulated, and we have the carrier and the sideband, while the lower part of the plot shows the corresponding PDH error signal. And so by varying the modulation frequency, as we are dealing with an offset locking technique and our sideband is the reference, we can both lock the cavity to the maximum of the resonance and also scan the frequency detunings up to several cavity line widths. And I have a movie here. I hope it will work well for everyone. And this movie here shows the results that we obtained when the cavity is pumped with 300 milliwatt of pump power and the crystal is at phase matching for second harmonic generation. In particular, the upper part of the plot shows the fundamental spectrum, while in the lower part of the plot there are shown the fundamental and second harmonic profile respectively. So the circles indicate that we are scanning the detuning and indicates the actual laser frequency detunings. As we can see, I hope anyone can see it, we have different types of combs in the correspondings of the different laser cavity detuning with different spacing and spectral span. So here there is a resume of the previous results and I show again these different types of combs that we can obtain depending on the detuning. But I would also like to highlight a different structure, a different type of emission that we obtained in the correspondence of this laser cavity detuning. And this is a simple structure made of just two sidebands at a distance of 16 nanometers from the pump. And we focused on this simple emission regime in order to perform our first measurements of quantum correlation. Interestingly, when investigated the spatial transverse profile of this mode, we noticed that it is not a fundamental cavity mode, but it is a higher order mode, in particular a TEM10 mode. And so concerning two-mode correlation, we know that Chi2 nonlinear processes are variable source of non-classical light, and in fact efficient squeezing has been already realized in Chi2 processes as second harmonic generation and optical parametric oscillation. But in particular, concerning the cascaded process of second harmonic and optical parametric oscillation, theory predicts the possibility to obtain squeezing in the difference between the intensity of the two side modes. And the squeezing factor relative to the shot noise is expressed by this formula, where F is the Fourier frequency, gamma is the cavity line width, eta E the escape efficiency, and eta D the detection losses. From this plot, we can see that when we consider the noise spectrum of the intensity different, it has a reduction with respect to the shot noise for frequencies inside the cavity bandwidth. And in particular, we have a perfect quantum noise suppression at zero frequency, while we have a finite noise suppression when losses are present in the system. And for frequencies higher than the cavity bandwidth, we reach the shot noise limit. This is the scheme that we used to observe two-mode correlations, in particular the twin beams, so the signal and idler exiting from the output coupler of the cavity are separated through the use of a diffraction grating and sent to a balance detector. So this balance detector is made of two identical InGaAs photodiodes, and in particular, in order to observe the correlations, we monitor the difference of the photocurrents through a spectrum analyzer. And these are the experimental results that we obtained. When we pump the cavity with 200 milliwatt of pump power, we have two signal and idler with 30 milliwatts of power per sideband. And the plot shows the spectral variance of the intensity difference, which is the red signal, compared to the shot noise, which is the light blue signal. And here the pink signal is the dark noise, so the electronic technical noise. So this plot here on the right has more details, and it represents the the spectral variance of the intensity difference normalized to the shot noise level, which is 0. So each time this curve is below 0, we have subshot noise quantum correlation. As we can see, these quantum correlations are present for frequencies up to 10 MHz, and in particular, we got a maximum squeezing of -2 dB in the correspondence of 700 kHz, and this is the level, when corrected for detection losses, results in a generated squeezing of -3.5 dB at the output of the cavity. So I come to the final remarks. I have shown in this presentation our results about optical frequency generation in quadratically nonlinear cavities, and so in different K2 systems as a singly resonant cavity second harmonic generation or a degenerate optical parametric oscillation. And in particular, I showed our latest results about frequency comb generation in doubly resonant second harmonic generation systems, in which we were able to observe also quantum correlation in a particular emission feature. I have also give you a brief introduction to the theoretical model that will be described in detail by Professor Wabnitz. And we are now working because we want to observe many mode correlation. So twin beams correlation that we have observed are just a prelude, and we hope to observe many mode correlation in a comb pattern soon. So I have finished. I want to thank my work group, my group leader, Maurizio in particular, all our collaborators. The project fundings has COMS and the Noise Joint Laboratory with Professor Adiari in Tel Aviv University. And I want to thank you for your kind attention.
Thank you very much, Iolanda, for your very nice presentation with very interesting results. And I'd like to invite questions from the audience. And if you want to ask a question, just please show me your hand. You should be able to see an icon at the top of your screen, and just with a hand symbol like this. So just press it, and I will make a queue from people who want to ask questions. Yes, please go ahead. You can type a question into the chat as well if you feel more comfortable doing it this way.
Yes, Marco.
Yes, thank you very much, Iolanda. Yeah, maybe I start with this. This mode correlation work was super interesting. Experimentally, how carefully do you have to control the parameters there, or how repeatable it is?
Okay, experimentally, you are talking about so the measurements of quantum correlation. We have to control, in particular, the stability of the emission of the sidebands. And first of all, they are very precise measurements in which you have to take in consideration and to lower all the technical noises that are present, and the crucial parameter is I think, is the definition of the shot noise level. I can come back to the presentation if possible. Yes. Can you see the screen?
Yes.
Okay. the most crucial parameter here is the definition of the shot noise level, and we have made many measurements in order to be sure that this data is stable and that we can repeat the measurement with the same result. I can see that we started from a comb emission which was very stable. So thanks to our locking system, the two sidebands are present. The intensity in the sidebands is stable, and also the frequency position of the sideband is stable. So we just looked, as I said, carefully to the DC level on the two photodiodes of the balance detection, and we calibrated this shot noise curve. And after repeated measurements, we obtained the same result.
Okay. So we have a question from Michael.
Yeah, thank you. So Iolanda, thanks for the talk. A quick question is just about the spectrum that you see for the noise. It's quite interesting to me that you have like large squeezing at like 1 megahertz or something, and then it disappears and stuff like this. So do you have any insight into why the spectrum looks like this?
If I understand well the question, you are asking me how this squeezing spectrum is linked to the frequency scale. How it's large? Yes.
So what I mean is, like at let's say 2.5 megahertz, you see no squeezing anymore, but then it reappears at 5 megahertz.
Yes, right. We are still investigating this aspect because in principle we are using a cavity, as we have shown here, that has in which we have a squeezing bandwidth of around 4 megahertz. So it's not strange that squeezing can also exceed a bit the cavity bandwidth. And for us, we are still investigating the fact that this squeezing has this shape, you are right, but maybe we think that it is linked in particular to the particular amplitude noise spectrum of the pump. And so starting from a particular shape for the amplitude noise of the pump, we have this shape of the squeezing, which is reducting the starting level of power. I don't know if I answered your question.
Yep. Thank you.
Thank you.
Yes, we have time for 1-2 more questions from the audience. If there are no more questions, Alex, yes, please go ahead.
Yeah, thank you very much for the presentation. I have a quick question about the theoretical model. Can you go back to the slide number 7?
Yes. This one?
No. Yeah. Previous one.
The previous one, yes.
No, sorry. It's the slide where you introduce boundary conditions for.
Yes, this one. So this one, the successive. Yes.
Yeah, and here I have a quick question about the second harmonic field B.
Yes.
Why theta2 equals to 1? Why do you consider that at each round trip it decays, fully decays?
Yes. In fact, okay. First of all, Professor Wabnitz will explain in details all these theoretical models in his presentation within a few minutes. Anyway, as I was saying before, this boundary condition can describe different types of nonlinear processes according to the parameters that we used. So, in particular, if we consider a singly resonant cavity, we have that there is we have the boundary condition for the oscillations of the fundamental fields inside the cavity, but for theta equal 1, it means that B is 0, and it is just saying that we have have no green radiation at the entrance of the crystal, because in this case we are talking about a singly resonant configuration in which the green field is not present at the beginning of the crystal, but it will be integrated and generated while the fundamental is propagating inside the crystal. If theta is different from 0, we have that is a doubly resonant configuration in which the green has its dynamics in the cavity and has oscillation similar to the fundamental power.
Okay, it means that if theta 2 doesn't equal to 1, you cannot obtain mean field equation for a single pump field.
Yes.